Hello again, physicists. Today's video is a quick recap of what we were discovering in class about sinusoidal nature of simple harmonic motion. So when we have a simple harmonic oscillator, like our mass spring systems that we've been studying, we can make a plot of position versus time, like we did in class using Logger Pro. Keeping in mind that position, if it's a vertical oscillator, it's the position of that mass in the vertical direction. If the oscillator is horizontal, then it's the horizontal position of that mass. When we make that plot, we see that the position of the oscillator as a function of time has a trigonometric behavior to it, like a sine or a cosine. And graphically, that this is what we end up with. And fittingly, it seems to imitate an oscillatory motion that we see. Now, the equation from that is that the position as a function of time was this. And now I'm going to dissect this equation and explain the different components that go into it. I'm going to start with this capital A, which is actually the amplitude of the oscillator. So A is the amplitude. Now, what this means, and this will tie into why we're using cosine instead of sine. At a time equal to 0, we are going to assume that the oscillator is being released from a point of maximum stretching or compression. And in fact, if you were to plug in 0 for t in this expression, that will make everything inside the cosine 0. And hopefully you know that the cosine of 0 is 1, which basically means that the position at time equals 0 will be the amplitude. So that's why we are using cosine instead of sine, due to the fact that we are assuming initially at t equals 0, the oscillator is being released from rest at its point of amplitude. Okay. The F that you see in there, you may already recognize that. That is the frequency of the oscillator. And if we were given an equation for an oscillation, we could find the period of that oscillation by using the fact that frequency is equal to 1 over the period. So we could take the number that would be in here for F and find period from that. And then obviously, hopefully, you would be able to know that t is standing for time. So there is everything as far as information you can glean from the equation itself. So you can just look at an equation for an oscillator's position as a function of time. And from there, you can figure out what is the amplitude of this oscillation, what is the frequency, or what is the period of this oscillation. And obviously, in addition to that, you could use this equation to figure out what is the current position of the oscillator as a function of time. Now let's look at the graphical component. So let's say instead of being given an equation, you're just given a graph of the oscillator's motion. And it would look something like the graph that you see here. Well, this can give you valuable information as well. Keep in mind that, again, at t equals 0, we are assuming that it has been released at a point of amplitude. And then as the oscillator travels over time, it will at some point reach a maximum displacement, which will be the opposite corresponding amplitude, like right here. That means that exactly halfway between those two amplitude points, you have your equilibrium point. And graphically, the equilibrium point will bisect your cosine function. So the green line that I've drawn in here, this is representing the equilibrium point for the oscillator. And then the distance from a trough, a maximum, or the distance from the minimum to that equilibrium point represents the amplitude of the oscillator. So what I just drew in here, that graphically represents the amplitude of this oscillator. Also, we could measure from the equilibrium point to the maximum displacement downward, which also would represent the amplitude. In addition, you can also get the period of the oscillator from the graph. The period will be essentially how much time it is for the oscillator to get back to the same position. So that could be the amount of time it takes to go from one peak to the next peak in the function, or it could be the time it takes to go from one lowest point to the next consecutive lowest point. This is commonly called peak-to-peak or trough-to-trough measurements, and either way you do it, it will give you the period of the oscillator. If you wanted the frequency, you could take that measured value and do 1 over the period. All right, so that's it for sinusoidal nature of simple harmonic motion. We're going to get a little more in depth with this on Monday, but that's all we really need to know for now. So the equation and the graphical representation and what information you can take away from each of those things. So until next time, physicists, until next time.